Okay, so what I'm going to prove now is that the sum of reciprocal primes diverges. What does that mean? That means that this sum, these are primes, 1 over 2 plus 1 over 3 plus 1 over 5, and I keep going all the way down. There's infinitely many primes. That this sum, even though it's an infinite sum, and I guess it's supposed to make sense in this case, but it goes to infinity, that this diverges. Now, how are we going to prove this? We're going to prove this by contradiction. We're going to say, assume that the sum converges. Okay, what that means is that the sum is going to go towards some fixed number. And once that's the case, we need to convince ourselves of a semi-difficult statement to believe in, but it is true that if it does converge, that if this sum really does equal some number, we can find some cutoff, some pj, right, the jth prime, such that the reciprocals after that are less than any quantity for any epsilon. But in particular, we could find some j such that all of the reciprocal primes after that j is less than 1/2. Okay, so if we assume that it converges, we're guaranteed to be able to find some j such that the reciprocal primes after that j are less than 1/2. This is guaranteed to be true as long as the sum converges. Now, after this, we need to sort of take a bit of what seems like a detour, and that's why I'm going to do it even in a different color, and we need to define a function. We need to say n, and I'll say sub j of x is, okay, the number, okay, so it's a count, the number of positive integers that meet two conditions, that are less than or equal to x and are not divisible by any prime greater than the jth prime. Okay, or p sub j, right? That's the way I say the jth prime, p sub j, right? Just another way of saying it. Okay, so the number, now getting a feel for what this function actually is takes some time, which is why it is that I'm actually going to do an example. So let's do an example. Let's take two examples. Let's say I said n sub 2 of 10 and n sub 3 of 10. So this is saying that this is going to be, what is this equal to by my definition? Let's fill in the particulars, right? The number of positive integers that are less than or equal to 10, right? X is 10 in this case, and are not divisible by any prime greater than the second prime. Or, in this case, 3, because 3 is the second prime. So let's count. So what are the numbers less than or equal to 10? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then which of these are not divisible by any prime greater than 3? Well, 1, is it greater than any prime greater? Is it divisible by any prime greater than 3? No, so this is in the count. 2, is 2 divisible by any prime greater than 3? No. Is 3 divisible by any prime? No. 4, is 4 divisible? No. 5, is 5 divisible by a prime greater than 3? Yeah, 5 is divisible by 5, so it's not considered in my count. 6, is 6 divisible by prime greater than 3? No, so it's in my count. 7, is 7 divisible by prime greater than 3? Yes, 7 is divisible by 7, so it's not in my count. 8, is 8 divisible by prime greater than 3? No. So 8 is only divisible by 2. Is 9 divisible by prime? No. So then this is in my count. 10, is 10 divisible by prime greater than 3? Yes, 10 is divisible by 5. So how many do I have here? 1, 2, 3, 4, 5, 6, 7. Did I count right? 4, 5, 6, 7. Yes. So n sub 2 of 10 is 7. This is 7. There are 7 positive integers less than or equal to 10 and are not divisible by any prime greater than the second prime, or 3. In this case, right, what would I have? Well, this is for 3, right? What's the third prime? The third prime is 5, right? P1 is 2, P2 is 3, P3 is 5. 5 is the third prime. So how many positive integers are there less than or equal to 10 that are not divisible by any prime greater than 5? Well, 1, is it divisible by any prime greater than 5? No. 2, is it divisible by any prime greater than 5? No. No, this is good. 5, is it divisible? 5 is now in the count. 6 is in the count because it's not divisible by any prime greater than 7. Is 7 in the count? 7 is the only one that's excluded in this case. 8, is 8 divisible by a prime greater than 5? No. Is 9 divisible by a prime greater than 5? Is 10 divisible by a prime greater than 5? No. So the answer to this one is 9. 7 is the only one that's excluded. Okay, and now right away, right after I sit here and get this idea here of what n sub j actually is, the next thing I need to sit here and think about is I need to put an upper bound in the general case in order to prove the theorem. So an upper bound for the general case, what we're going to say is going to say let n be a positive integer that is, and it's going to meet two conditions, right? Less than or equal to x, and it is not divisible by any prime greater than p sub j. Okay, now, well, this is just some n in this count n sub j of x, right? This is any n, okay, that is in that count of n sub j of x, right? Like in this case, right, let's take this here, right? 2 was in there, right? Because 2 was less than or equal to 10, and it wasn't divisible by any prime greater than 3, right? Because this is the second prime in this case, okay, and so forth. So this 2 could have served as the role for n. Now, I want to come up with a maximum possible number of n that could be in n sub j of x, okay? So the way I'm going to say this is that, right, if I have some n, we need to remember now, if I have some n that meets this criteria, right, that means that it's in the count of n sub j of x, okay? I can rewrite n. I could write it as this. It's going to help us if we first see that n is going to be equal to p1 to the q1 times p2 to the q2 times ... all the way down to p sub j to the q sub j. Now, this here, right, as long as I allow for q1 through qj to possibly be 0, n will always be of this form. N, well, it could have like p sub j1, but this is guaranteed to be 0. All of the primes over here, anything greater than the jth prime, we know that this n is not divisible by any prime greater than p sub j. So that means that this has to be a 0 for any p sub j plus 1, p sub j plus 2, p sub j off into infinity. All of those exponents would have to be 0. Okay, and this here, as long as we allow for zeros in the q1 through qj, this is how we could express any such n in this count of n sub j of x. So this is again any n in this count. Okay, so what do we know? We know these two things. Okay, blah 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 blah. Now we're here. If it's the case that we have this, right, where we allow the q1 through qj to possibly be 0, what we can further do is I can take any of these exponents that are greater than 1, and I can pull them into here. I can pull them into some bin. So I can pull all the things that have an exponent greater than 1 and then pull everything else over here. What do I mean? Let's do examples. So let's say I had n is equal to, let's say I said n was equal to, I don't know, 3 to the 5, 7 to the 11, and then, I don't know, 13 to the 4th, and then times 17 to the 1. Okay, what I can do here with this n, if whatever n is going to be, I don't know what j is in this case, but it doesn't matter. The idea is that you could always take this number and make it so this number over here is what's known as square free. Now, what is square free? You want this number over here to be square free. So, how do I do that? I can take from this. There's going to be some prime factorization of n. Every single number has a prime factorization. Let's say that this is the prime factorization. We know that it doesn't involve any prime greater than the jth prime in its prime factorization. And then I have that I could do this. 3 to the 4th, 7 to the 10, 13 to the 4th, and then I'm going to put everything else over here. So what was left? I still have that 3 to the 1, right, to make it 3 to the 5th. I still have that 7 to the 1. The 13 to the 4th becomes 13 to the 0. I don't have any more 13s. And then the 17 to the 1 is over here. This number is square free, what I was saying over there. This number is square free. And I'm going to keep going with this. I'm going to show you what I mean by being square free. But this number is a perfect square. This number can always be written as 3 squared, 7 to the 5th, 13 to the 2nd, the whole thing squared, right? You should see that these two things are equal. And then this number is square free. 3 to the 1 times 7 to the 1 times 13 to the 0 times 17 to the 1. Okay, what does it mean for it to be square free? It means that it has no perfect squares as factors, no perfect squares as divisors. If any of these exponents were greater than 1, then it would have a perfect square as a divisor or a factor. And that's a key point, right? So the only exponents that I could have in this part of the number, in the square free part of the number, would be 0 and 1. Now, if I sit here and I go like this and I take this in the general, what this means is that I can rewrite n like this. I could say n is equal to n1 squared times m, where m is square free. And again, the key here is that this number, this m, okay, when you write it as a product of primes, none of the exponents will be greater than 1. Now let's pick back up. Let's go to a new page. Let's see what we got. Let's see. No, not what I want to do. Not what I want to do. What do I want to do here? There we go. Okay. Okay, so let's go back. Let's say I have n is equal to n1 squared times m, where we know m is square free. And we also have a whole bunch of other nice facts about n as a whole. Okay. So n as a whole, we know, is not divisible by any prime greater than the jth prime. So that means m is not divisible by any prime greater than the jth prime. M is always going to be of the following form. M is always going to be P1 Q1 times P2 Q2 times P3 Q3, whatever, dot, 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 all the way down to PJ QJ. Okay? And each one of these Q1, Q2, Q3, Qj, all the way down, can either be 0 or 1. This means that there are 2 to the j possible choices for m. Okay, so how many choices for m? 2 to the j. How many possible m? 2 to the j. That's what this question's answering. Sorry, 2 to the j. Okay, so I have that fact. Now let's look at n1. If I minimize m, then I maximize n1. Minimizing m, right? And I don't know whether m is a minimum, I don't know. But if m is a minimum, then I have that this here is going to be the square root of n is equal to n1. Then I have something further, that n is guaranteed to be less than or equal to x. So the square root of n is less than or equal to the square root of x. So now putting this all together, right, this is maximizing n1. Max n1 is this, right? If this is the case, m is a minimum, maximizes n1. This forces this fact. Okay, and this is again the maximum value for n1 is equal to the square root max value, max n1. So n1 is guaranteed to be less than or equal to the square root of n, but we know that the square root of n, this is the other way around. We know that n1 is less than or equal to the square root of n, but we know that the square root of n is less than or equal to the square root of x. This just comes down into that n1 has to be less than or equal to the square root of x. And I have, at most, the square root of x possibilities for my choice of n1. Okay? Most possible n1. How many possible n1 do I have? I have at most the square root of n1. Together, n1 and m will completely define this n. So you have at most that the number, at most, the square root of x times 2 to the j, possible n. Okay, which is the same thing as putting a bound on this n sub j of x. And with this being said, we're almost there at what we wanted to prove originally. So let's get another one. Let's see what we got. Let's go and let's reiterate everything if we can. So now I go back to this statement here. I have that 1 over p sub j plus 1 over p sub j plus 2 plus 1 over p sub j plus 3 plus ... is guaranteed to be less than a half. Now, I also have that the number of positive integers less than or equal to x that are not divisible by a prime greater than the jth prime is guaranteed to be less than the square root of x times 2 to the j, less than or equal to. Now, let's investigate a general statement. Let's cut this over here and let's investigate something else. Now let's say, how many integers, or positive integers, again, always going to be talking about positive integers are there less than or equal to x that are divisible by some prime p. Okay? So how many positive integers are there less than or equal to x that are divisible by p? So pick numbers for x. Let's say x is 20, I don't know, and then p is 7. Okay, how many positive integers are there less than or equal to x, less than or equal to 20 that are divisible by 7? Well, if you sit here and you think for a second, you'll see that it's actually 20 by 7 is the most, right? At most, the answer to this is at most 20 by 7. And you could switch. You could try, I don't know, x to being whatever, 30, and then this to being another prime, 11, right? The answer would be at most 30 by 11, right? How many are there? There's actually 2, right? In this case, there's 2, right? In this case, there's 2, but this is a little bit more than 2, right? This is greater than 2, this is greater than 2, but in both cases, the answer would be 2. How many positive integers are there less than or equal to 20 that are divisible by 7? There's 2, there's 7 and 14. How many positive integers are there less than or equal to 30 that are divisible by 11? 11 and 22. But in this case, yeah, there is at most, so this is a little bit more, this is a little bit more, okay. But in general, right, x and p, the answer is at most x by p. Okay, and take your time to convince yourself of that fact. With that, I ask another question that I will probably just go on to another page for again. So let's get another page and let's see what we got here. So let's go womp. Okay, and I'm gonna say how many, let's ask this question. How many positive integers are there less than or equal to x, less than or equal to x that are divisible by some prime greater than p sub j. Okay, and now let's take our time with this question because this question is our bridge. Okay, we're bridging things now. So how many positive integers are there less than or equal to x that are divisible by some prime greater than p sub j? In this case, right, how many primes are there at most less than or equal to x that are divisible by p sub j plus 1, right? Let's look at the last thing that we just did. Let's go back. We said that how many positive integers are there? Positive integers are there less than or equal to x that are divisible by p sub j plus 1, right? Well, in that case, it would just be p sub j plus 1, right? P sub j plus 1. This is at most, right? How many primes are there less than or equal to x that are divisible by p sub j plus 2? Well, x over p sub j plus 2, right? How many primes are there less than or equal to x that are divisible by p sub j plus 3? This many, right? So at most, going back to the other question, right, if we could sit here and keep this in our minds back and forth. Okay, how many primes are there how many positive integers are there less than or equal to x that are divisible by some prime? Well, how many positive integers are there less than or equal to x that are divisible by p sub j plus 1? At most, x over p sub j plus 1, right? That's how many positive integers there are less than or equal to x that are divisible by p sub j plus 1. Plus, okay, at most, the answer to this is at most x over p plus x over p sub j plus 2 plus x over p sub j plus 3 plus ... so forth. And we get a similar sort of sum that we had. So the answer to this is at most, the answer to this question is at most this sum, this infinite sum. Then what is this exactly in terms of our other function? Take your time with convincing yourself of this statement. This is x minus x sub j of x. Okay, we should see that the number of positive integers that are less than or equal to x that are divisible by some prime greater than p sub j, plus the number of positive integers that are less than or equal to x that are divisible by some prime that are not, right? This is how many primes are not divisible. This is how many positive integers that are not divisible by some prime greater than p sub j. So the number, if I do x minus, that's what's left over, okay? This is what's left over from x, right? And this then means that this is at most. So x minus j is less than or equal to x over p sub j plus 1 plus x over p sub j plus 2 plus ... off into infinity. And if I go back to one of these, we see this. Yes, I'm going to take this fact. So I'll call this 1, and then this one 2. So I take this fact 1, and I go back, and I say, or let's look at this. Let's just look at this here. If I multiply by x everywhere on both sides of this inequality, the inequality will stay true. So I get a new inequality down here. X over p sub j plus 1 plus x over p sub j plus 2 plus ... is less than x over 2. And I need to use this fact here because this sum is the same thing that I have on the other page. I have that this sum is guaranteed to be less than x over 2. And then putting these two together, I forget about this here. I have x minus x sub j of x is less than x over 2. And then what I do is I'm going to solve it for n sub j. And what I'd get is I'll get that n sub j, I get x over 2 is less than n sub j of x, right? When I minus the x over 2 on both sides, this becomes just x over 2, and then I add the n sub j over to the other side, I get this inequality. And now I use the other fact that I got, which is this, I got this fact right here, that n sub j of x is less than or equal to the square root of x times 2 to the j. So this is less than or equal to the square root of x times 2 to the j. And I forget about this piece in the middle, and I get this inequality, which is gonna lead to my contradiction. I got x over 2 is less than the square root of x times 2 to the j. If we solve this for x, so what would I do to solve it? I guess I would square both sides. I don't know. Whatever is going to be the fastest way, I'm not too sure. 2 to the j is less than, I square this side, I get x squared over 2 squared. I divide by x on both sides. I'm going to get x over 2. I'm going to get x over 2 squared is less than 2 to the 2j. And then I multiply by 2 to the 2 on both sides. I get x is less than 2 to the 2j plus 2. And this is a contradiction. Why is this a contradiction? There was no bound on x. X is any number. Okay, x is any number from the very first one. So since x is any number, there can't be a bound on x. Integers less than or equal to x. Any x. Doesn't matter. So here, in this last one, now I'm saying that there's a bound on x, which is a contradiction. You can't have this. It doesn't matter what j is. It doesn't matter. There's no way that there could be any bound on x. And that's your contradiction.